Okay, good morning. Welcome to the session on dynamics and control. My name is Frank Park. I'll be chairing the session. So we've had sessions on optimization and control. Sorry, I said dynamics and control. I meant optimization and control on and off at ICRA for at least 2 decades now, if not more. And I can unequivocally tell you that the talks you hear today are going to be quite different from the talks you heard maybe 5 or even 3 years ago. So if there were a unifying theme, I think to the 4 talks you hear today, it's that they all address the elephant in the room, namely the belief that foundation models, LLMs, VLAs, whatever, are going to solve all of our problems. I think you'll see throughout the next 4 days healthy debates on whether scaling and end-to-end learning in general are feasible in the near term for robotics, at least in the practical sense. And this session, I think, kicks off that debate. And we have 4 very talented and experienced roboticists who I believe all share a healthy skepticism about the practical feasibility of scaling end-to-end learning. So they're all at the forefront of research in robot learning, and they have firsthand experience on the challenges and limitations of just throwing data at basic foundation models or using foundation models in practice. So Ram Vasudevan from University of Michigan is going to kick things off by examining sort of the disconnect between the impressive demos we see today of vision language foundation models and recognizing and classifying images and videos, and why they're still mostly unusable in real world environments. So he'll argue that model-based control is in fact the key to making these VL foundation models work reliably, offering guarantees and interpretability where applicable. Our next speaker, Jana Tomova from our KTH in Stockholm, is then going to talk about formal methods. First, she'll tell us exactly what formal methods are. And then she'll tell us a little bit more about a particular method called signal temporal logic, STL, that she's been working on and how they can offer formal guarantees and quantitative measures of robustness. Following Jana, we have Todd Murphy from Northwestern. He's going to talk about robot learning in isolation. So, this doesn't mean locking up a robot in a room and telling it to learn, but rather what a robot can learn just doing various incidental tasks. So Todd is going to show how methods from statistical learning and optimal control can help a robot to learn in this fashion. And then to conclude the session, we're going to have Angela Scholik from TU Munich, who's going to follow up Todd by telling us about her work on how robots can learn from their own data. And like the other speakers, Angela relies on model-based control theory and formal methods to achieve these goals. And she's going to have a particular focus on safety. And she's going to show us a lot of case studies involving robots and drone swarms. So each speaker is going to have 12 minutes, and we've set aside 3 minutes at the end of each speaker's talk to allow you to ask questions. So without further ado, I'm going to ask Ram to kick things off.
Okay, so thank you all for coming. I'm going to talk today, I think, about the elephant in the room, as Frank described it, which I think has been maybe the place that has seen the most excitement in robotics in the past several years, which is vision language action models. And so for those who don't know what these are, I think this video from Google actually does a really nice job of describing it. So before I play it, the way that these models work, or this way that the system is going to work, is essentially someone is going to describe a task here, and then the VLA model is essentially going to interpret that task, that language, and basically turn it into a sequence of actions here. And so here we see move banana to a water bottle, and the robot is able to complete it. And in fact, now we see a slightly different task where the banana is moved to a completely different location. And in fact, it's not just banana. This can operate on all sorts of different fruits, obviously. And here's an illustration of that as well. The important thing here is that these VLA models are really exciting because they can basically turn our language into a sequence of actions directly that the robot can then act on, right? So the question is, how does this work? And I thought it would be appropriate, since we're in Atlanta, to choose 2 stars of pop for our instructions here. So in this instance, we're going to ask the robot to move a can to Taylor Swift. And in fact, what ends up happening then is that this information gets passed to these pair of encoders, which are basically going to translate this high-dimensional data into some sort of encoding, which is then going to get fused together and passed to some action decoder, which is then going to generate a sequence of actions, which are then going to be successfully passed to the robot, and the robot is then going to be able to move this can, and everything works so nicely, right? Now, these models are really impressive, and the natural question you may ask is, how do we actually train these models? And the answer is relatively straightforward. It is data, right? And when I say data, I mean lots and lots and lots of data. In fact, so much data that, in fact, we need an internet scale level of data. And what I mean by that is millions of demonstrations in order to actually be able to complete this task successfully, to learn how to do this task. In fact, this is pretty difficult and requires a lot of data analysis to actually be able to do cleverly. So you may be asking the question of, well, why do we spend so much time thinking about this problem? Well, the exciting point here is that basically we can take these models and immediately generalize. And so just as an example here, we've asked these pair of robots from Figure to essentially put away objects that they've never seen before. And again, this is impressive because basically this doesn't seem to actually exist inside of the data set used to train these models, and nevertheless they're able to complete these really complex tasks and coordinate with one another to actually be able to do it. Notice, we never described where to put the objects away. In fact, it's figuring that out on its own, which is amazing. So these videos has created an avalanche of excitement. In the past several years, you've seen hundreds of papers on VLAs, and essentially everyone and everyone's mother is essentially working on this. One of my students described it as literally 5 years from now, everyone on planet Earth will have written a paper on VLAs at the rate we're going, right? Now, you may think to yourself, if it's working so well, why do we need to continue writing papers? Well, there are some problems with making these models work, and broadly, they can be categorized into sort of 3 different groups. The first is really understanding basic physics and contact physics, really. So for instance, I may ask to move this plate onto the counter, and because I haven't really modeled the contact well, what ends up happening is as I move this object, I run into a collision. On the other hand, there are other problems not associated with the physical model itself, but the way that we see the world. In this instance, there's a distractor, which is this, cleaning device next to our eggplant, and that actually confuses the model and allows it to fail here. There's a third example, and maybe most interesting example. We have this question again, place this box inside the drawer, or query. And in this instance, the robot begins, it picks up the box, and then it realizes, oh shit, the box actually needs to be first, I need to open the drawer first, and then put the box inside of it in order to complete the task, and it gets stuck in this instance, right? So these models, they're really exciting, but I'd argue that they're really creating a fork in the moment for robotics writ large. On one side, we have sort of the solution we've been exploring sort of loudly up to this point, which is, the problem is really more data. We need more and more data, and data will solve all the problems that exist out there. And in fact, at that point, I would assert, if we continue to push this line in this sort of demanding way, we're going to arrive at a point where basically ICRA 2035 is going to be no different than an NVIDIA GTC-style conference, where we're basically pushing GPUs on everyone to solve all the problems that exist out there. In fact, what I'd argue is that as an optimization and controls community, we need to evolve here and start answering some harder questions associated with how to make these models more transparent. And in fact, that's what I'm going to speak about for the rest of my talk here. How do we build this kind of transparent autonomy? Now, at this point, you're probably thinking to yourself, this old guy standing on the stage screaming about VLAs, that seems pretty depressing. Like, that isn't that interesting. This is the hot new topic. We should be working on this. And in fact, the point I want to make here is I'm not that old. I have a lot of black hair. And in fact, we need to not think about dismissing VLAs. We need to think about how to take leverage of VLAs and figure out why they're working, right? And that's the challenge that I want to put forward here to our robotics community, and specifically our optimization and controls community, which is we should think about how models can play a role inside of VLAs to make them work better. And in fact, the thing most people think about when they think of models is to simply use them as shields. And what I want to argue is that shields, that's not the right way to think about models, especially in the VLA world. So what is a shield? Well, suppose I have my robot here, and it needs to get to some goal pose. Well, maybe my learning-based algorithm, sees that there's an obstacle out there and basically generates a sequence of waypoints that it passes to the robot. So maybe that looks a little bit like this, and those waypoints are passed to the robot. Well, traditionally, I would detect, for instance, that this robot's arm is in collision, and I would say, well, look, I need to put in a model-based safety shield, and that safety shield is just going to do the following. It's going to figure out if that arm is in collision, and if it is, I'm going to start relying on a backup planner here, and that backup planner could be something as simple as just bringing the robot to a stop. Now, that's a really interesting device. It's the way that we as model-based folks typically think about things. But the point I want to drive at is that through a series of papers, people have realized fairly clearly that this just encourages really short-sighted thinking and generally leads to suboptimal behavior. We shouldn't be thinking about models as an afterthought. We should be thinking about them in the context of VLAs. And in fact, that's what I'd like to get to, these 3 problems that I think we need to solve as a community to get beyond the demo. So the first is figuring out numerical tools that can allow us to actually quantify learning error. Why is that useful? Well, it allows us to basically take our model and dial in a confidence that will allow us to actually reason about how these VLA systems can play well with the things that we actually care about in the real world. So as an example, one of my students is actually going to be presenting a paper on Thursday using a technique to actually do this type of quantification that's called conformal prediction. The way that conformal prediction works, for instance, is you could imagine that my action decoder is taking a particular encoding, and it's basically a type of neural network that's predicting a swept volume in this instance, right? The way that conformal prediction works is it tries to characterize the error made by these neural networks and essentially describe that as a type of quantile error that can then be appended onto the model in a way that accounts for that error, right? The interesting thing here is that red set now accounts for the error that the neural network is making in probability, and in fact, it's a differentiable representation that can then be passed to other types of optimization procedures like this one here. If you head to that talk on Thursday, you'll see that, in fact, we've actually not only been able to deploy this in simulation, but actually out in the real world. So the problem with these methods so far is that they aren't really able to deal with an open vocabulary. That's what makes VLAs really exciting. And these techniques so far really are really sort of limited to dealing with a fixed vocabulary at the moment. The second challenge I want to talk about is how do we actually take physics and perception models and actually incorporate them in a meaningful way into learning. Now again, if we could do that, it would allow us to safely generalize the way that these VLAs are working because we would have a representation that could essentially be backpropagated through in order to actually improve the way that learning occurs. So in fact, here's a really fun paper that just got accepted to TRO yesterday by my students, where essentially what they do is show that they can operate directly from images to construct a normalized representation of the environment as a set of Gaussian splats. So what they can show is that these Gaussian splats essentially correspond to the probability that a particular location in the scene is actually occupied. And in fact, the really exciting thing is they can turn that representation into something that they can then plan on. And again, all of these bits of this representation are actually differentiable, which can then be added on to the way that VLAs work in order to train them in a much more meaningful way. So this is great. But if you looked really carefully, you would see that, in fact, we weren't actually doing any contact-based manipulation. And the alignment between that contact and the actual state of the world is a non-trivial problem unto itself. And in fact, that's a thing that I would argue we need to spend a lot of time thinking about. The last point I want to get at, and maybe the most exciting point, is not to just think about how to append model-based control inside of this VLA box, but to take our model-based control techniques and start thinking about why VLAs are actually able to generalize. So if I could understand exactly the type of data it would take to actually make my VLA work better, I wouldn't need millions of examples in order to train my data, or train my model. I could actually target my data to actually train my model in a more sort of efficient fashion. Now, the thing I want to point out here is very little work has been done in this area, and in fact, most of the work in VLA generalization has simply been empirical in nature. Some company, some research group deploys these systems and sees that they work really well, and that's it. So I want to come back to this slide here. We're really at this fork in the road moment for robotics. I've described this transparent autonomy side, but the other side, I would argue, shouldn't just be dismissed kind of in the way that I did. And in fact, I think the loudest voice speaking for the other side belongs to a Turing Award winner in this, paraphrased quote by Richard Sutton, which basically describes, a lesson learned over and over by AI enthusiasts, which is AI methods that exploit massive computation and data eventually beat methods that embed detailed human domain knowledge. It's a really interesting point. The one thing I would point out is that when it starts coming to safety, it's unclear if this type of lesson that Richard is speaking about here has actually applied as well as he claims. These 3 articles they're from the past 6 months. These 3 things are actually using lots and lots of data, right? So it doesn't seem obvious that lots and lots of data are going to solve these types of problems. And in fact, I would point out that it feels like we have a little bit of a blind spot when it comes to actually thinking about safety, especially in the age of AI, which is we think that AI performance scales with data, and that means that safety will also scale with data. But in fact, our lessons to date don't make that so clear. So I'll end with these 3 problems. I want to thank my students and colleagues who've helped in this presentation, and then my sponsors. Happy to take any questions.
All right, thanks, Ram. I saw a lot of heads nodding in agreement. So we have about 2 minutes. Questions for the speaker. We have mics set up. Well, there's a question online asks whether physics-informed neural networks are useful in.
Yeah, so physics-informed neural networks are really interesting. I think they're a nice mechanism to think about these types of problems. The one thing I would say is, in a lot of these robotics examples, we actually do understand the physics relatively well. So it doesn't seem obvious to me why we would need to move directly to a pin in order to actually be able to leverage this knowledge. But I'm happy to hear otherwise or discuss that further.
Hi, we have a question.
So we talk about how these vision language models and large language models can generalize, but they're also trained on internet scale data. So are they really generalizing, or are they just, inferring from things that they've seen in their training data because the data set is so big?
That's an excellent point. The thing I would assert here is mostly empirical observations by users. It's unclear if, for example, some of the testing set has somehow seeped into the training set in the way that you're describing. That could very well be the reason we're actually seeing generalization, and people just have not investigated it carefully enough. That is something that I do think we should spend more time thinking about. And in fact, in the VLM world, in the LLM world, we've seen that actually that kind of data seepage has truly been a pretty serious problem when it comes to evaluation.
Okay, maybe we'll take just one quick question from him.
Yeah. A question about safety. I'm just wondering, safety sometimes can also be used to keep the bitter lesson away from us. In other words, let's say self-driving cars already are safer than humans. Maybe how do you quantify safety so it's not just an excuse for not adding, bitter lesson methods?
Yeah, so I'm not, the thing I would say is, I'm not dismissing the idea of using AI. Again, my disclaimer here is I actually think these methods are extraordinary and are pushing us to think harder about the ways that we should apply model-based techniques. My only retort back to what you're describing here is it seems as if it's a foolish exercise from an ethical perspective for us to basically say, well, in an attempt to eventually build a safer system, we're going to deploy a really unsafe system on people that may get into accidents and get into trouble, right? So again, there's a right way to scale here, and I think when we think about safety in particular, we should be scaling in the right, in the ethical way.